In the second part of section 4.3, we will now look at expanding and condensing logarithmic expressions using our three rules that we learned in the first part of the chapter. So feel free to refer to the logarithmic properties handout. And again, you'll see this is our product rule, this is our quotient rule, and this is our power rule. And we can use all these rules in combination when expanding a logarithmic expression. Let's look at expanding logarithmic expressions. And we'll start with example 4 on page 496. And again, in these problems, we can sometimes use all of those individual rules that we've learned to expand the logarithmic expression. So in part A, we have log to the base b of x squared times y. Now, initially, we're going to use the product rule. If you look, we have x squared times square root of y. This would be our capital M, and this would be our capital N. So we'll initially use the product rule to expand it to log to the base b of x squared plus log to the base b of square root of y. But notice, we still have exponents to deal with our x term and our y term. So we can rewrite the expression slightly. This will be log to the base b of x squared plus log to the base b of y to the 1/2 power. That's really the change I wanted to make, was change that radical expression to one with rational exponents. And now we'll apply the power rule. And this will now be 2 log to the base b of x plus 1/2 log to the base b of y. When you finish, when you're expanding these expressions, your exponents, whatever letters they are, should be just the singular letters, such as x and y, as you see here. You should have made sure that there were no remaining exponents that you didn't change using the power rule. In part B, we're given this expression, log to the base 6 of the cube root of x divided by 36y to the 4th. And this is a little more complicated problem, but let's start off with the basic rule that we need to use, which is the quotient rule. Notice we have an expression here in the numerator, which we would refer to as capital M, and then an expression in the denominator we would generically refer to as capital N. So let's first decompose this expression using the quotient rule. So this would be log to the base 6 cube root of x minus log to the base 6 of 36 y to the 4th. Now, we will have to apply the power rule to this expression to finally be done with that part of the problem, but one thing that makes this problem a little more intricate is there is sort of a nested product rule within the greater quotient rule. So if we look here, there's actually a product, 36 times y to the 4th. So we're going to need to apply the product rule to continue expanding that expression, and I'm going to add grouping symbols just to make sure I don't make a mistake with the final expression. As we continue to simplify the expression, notice this cube root of x is really x to the 1/3 power. So then we'll apply the power rule, and then we can be finished with that term. So that will be 1/3 log to the base 6 of x. But now we have this nested product rule we have to deal with. So now we'll have log to the base 6 of 36 plus log to the base 6 of y to the 4th. But now we can do some further simplification within those brackets. So as we continue simplifying, it will be 1/3 log to the base 6 of x minus, now notice we have, this is base 6. 6 to what power gives me 36? Well, 6 squared is 36. So that whole piece can evaluate to 2. And then, of course, this negative sign will make that negative. And then when we look here, we will have the power rule to use, where this exponent of 4 is going to come out front as a multiplier, but then it will also be made negative as we distribute that negative sign. So this will be minus 4 log to the base 6 of y. So this will be your final answer. Notice how I used the grouping symbols to make sure that I captured this negative sign, which gets distributed over both terms as we use the product rule within those brackets. Now do pencil problems 4A, 4B, and 4C. When we expanded logarithmic expressions, we used our product, quotient, and power rules as you saw them here. And as long as our quantities m and n are greater than 0, these rules are satisfied and we could expand logarithmic expressions. When we condense logarithmic expressions, we're going to do this process in reverse. So you see here, the rules really look like they've just been switched from this section above. So now, a sum of two logarithms we can collapse or condense using the product rule, or a difference of two logarithms we can collapse or condense using the quotient rule. And with the power rule, we can take a multiplier p that is out in front of a logarithmic expression and now move it back into an exponential form where we have log to the base b of m to the p power. When condensing logarithmic expressions, although the product, quotient, and power rules are the same rules we use when expanding logarithmic expressions, there is one extra item you need to keep in mind, and that is the coefficients of your logarithmic terms must equal 1 in order to condense them using those rules. It's not something we have to be concerned about when we expand logarithmic expressions, but it is a difference when you condense. So keep that in mind as you work on these problems. Example 5 on page 497 of your textbook has us condense this logarithmic expression, log to the base 4 of 2 plus log to the base 4 of 32. Now, this is sort of a simpler form of this problem, but notice the coefficients of the log expression are equal to 1. So we can now immediately condense. So this would be log to the base 4 of 2 times 32. But always see if you can evaluate that further. That's log to the base 4 of 64, but notice 4 to what power gives me 64? Well, that value is actually 3. 4 cubed is 64. So, depending on the numbers you have in your problem, sometimes you can do a final simplification of the expression. So always check whether that's possible. In part B, we're given log of 4x minus 3 minus log of x. Again, this is a simpler version of a condensing problem where the coefficients of the log terms are already equal to 1. So we can now use the quotient rule to immediately condense this into a singular expression. So this will now be log, and now we will have a quotient of 4x minus 3 divided by x. In example 6 on page 498, now we're given this expression, 1/2 log of x plus 4 log of x minus 1. Unlike example 5, now notice that our coefficients are not equal to 1, so we cannot immediately condense. What you need to do is start with the power rule and use it in reverse to first move these multipliers back into their exponential position, and then we can condense. So this will be log of the x to the 1/2 power plus log of x minus 1 to the 4th power. And then when we finally condense that expression, you can either express it as log of square root of x times x minus 1 to the 4th, or if you wanted to, you could leave it as log x to the 1/2 times x minus 1 to the 4th. Those two forms would be equivalent. But again, make sure, use that power rule in reverse to make sure you have coefficients of 1 before then using, in this case, the product rule to condense the logarithmic expression. Part B, we have 3 times natural log of x plus 7 minus natural log of x. Now this second term does have a coefficient of 1, which is fine, but this one does not. So again, where we'll start is we're going to use the power rule in reverse. This will be natural log of x plus 7 cubed minus natural log of x. And now, because of the subtraction symbol you see here, I'm going to use the quotient rule. And so we can express the condensed expression in this form. Natural log of x plus 7 cubed divided by x. In part C, we're given this expression, 4 log to base b of x minus 2 log to base b of 6 minus 1/2 log to base b of y. Again, none of the coefficients of those logarithmic terms are 1, so we must use the power rule in reverse to make those coefficients 1. So this will be our first step. This will be log to the base b of x to the 4th minus log to the base b of 6 squared, which would be 36, minus log to the base b of y to the 1/2 power, which we can also write just as square root of y. And now what you can do is look at these symbols carefully. You see that we have subtraction symbols in front of both of these terms. That means they're really going to go in the denominator using the quotient rule. So our final expression will be log to the base b of x to the fourth divided by 36 square root of y. Now, do pencil problems 5a, 5b, and 5c. The last topic we will look at in section 4.3 is a small one, but it's important, and it's known as the change of base property. Remember how we started off our introduction with logarithms, and we said that any numerical value could be expressed as the combination of a base to an exponent. And so the change of base property allows us to calculate that exponent for any given base and any given value. Now, if you've looked at your calculator, you might notice that you really only see two buttons. The common log button, which is base 10, and the natural log button, which is base e. But there really are an infinite number of possible bases. And there are many other numerical systems that use a different base. For instance, computer language or binary language is a base 2 system. Hexadecimal is a base 16 system. If we want to calculate the logarithm for any base and any value, and we only have the common log or the natural log buttons on our calculator, how do we do that? Well, that's where the change of base property comes in. And it says the log of any numerical value m for any base b can be calculated really two equivalent ways. We can either use our common logarithms or our natural logarithms. So log to the base b of m will be log of m divided by log of b. So you can use your common log button if you'd like. But you can also use your natural log button. Notice the formula is essentially the same. Log to base b of some value m will be natural log of n divided by the natural log of b. When you use the change of base property, you can use either the common log or the natural log. So let's look at example 7 on page 499. We're asked to calculate the log of 140 using base 5. So we can really set this up a couple ways. This could be common log of 140 divided by common log of 5, or natural log of 140 divided by natural log of 5. I can use my built-in calculator to calculate this expression with the log and natural log functions. So I'll do 140 log divided by 5 log. We'll get that value 3.0704. And let's do the natural log. 140 natural log divided by 5 natural log. And again, we get that same value. So this is our final answer. Going to 4 decimal places, it'll be approximately 3.0704. Now remember that relationship we have of base to an exponent equals a value. So to see if your answer is right, you can take your base, in this case is 5, and raise it to this exponent. Although there could be slight rounding, the value you get should be very close to the numerical value that you started with. So let's try that. I'll take 5 and I'll raise it to the power of 3.0704. And notice, of course, it's almost exactly 140, right? We can expect a little bit of rounding error here, but clearly that's the value of 140. So we know our answer is correct. Now do pencil problems 6a and 6b.